the amps. I wanted to go through some of the subsystems just so you understand the basic layout of it. We've got our main high-level controller up here. This is where the user interacts with the system. This is where I generate the torque profiles and monitor the signals that are coming in. This communicates with both the data acquisition system down here in the abdomen and the Robotech motor controller that actually goes out, sends the commands directly to the motors themselves. We measure torque output, or we estimate torque output, I should say, using these current sensors that are mounted on the biceps. Since we know that current and torque are proportional, and we've determined that proportionality constant, we can measure the current flowing through each motor to estimate the torque output on each wheel. The other signal that we measure comes from the drive wheel encoder on either side. This tells us the instantaneous position of the wheel, and then as the system moves, we can track those differences in position to figure out the velocity of the wheel and the velocity of the overall system. So in summary of this section, I've showed you the validation of the current-based torque control of the motors in both stationary and in overground motion. I've shown you our generated maneuvers that emulate different parts of wheelchair motion in both rectilinear or straight motion and curvilinear or slalom serpentine motion. And this system maintains that same output metric, that propulsion cost that I went through earlier. And this augmented amps is specifically designed to mechanically and objectively measure the performance or propulsion cost of various wheelchairs across many different design choices. I want to take just a brief period of time and go through our outcome variables. We identified 4 for all of the studies. Again, the torque is what we hold constant. This is what you saw when I generated the maneuvers. This is what we're sending into the wheelchair from the amps. So for this torque profile, for this particular test, the chair exhibited this motion, this velocity. So the first outcome variable is distance. And this is represented by sort of just the area under this curve. Velocity is in meters per second. We multiply that by the seconds of the maneuver to find the total distance that it traveled. Right? Just integrate along this line. Propulsion cost, as I went over earlier, is found by multiplying our wheel torque and our wheel velocities to get power, and then integrating that in the same method over time to get the representative work plot, or the total amount of energy that we supply, the cumulative amount of energy that we supply to the system throughout the whole maneuver. We then divide that end work value by the total distance traveled by the center of mass. The third is the max attainable kinetic energy. This represents sort of just a combination of all of the motion in the system. The motion being the output of the wheelchair, the input being the pushes, the torques from the motors. So we were using this as a way to relate the output, the energetic output of the system to the input. And we use a series of equations that I'm not going to show here, but in general, we take a look at the rolling of the drive wheels and the casters, as well as the swiveling motion of the casters and the entire wheelchair itself as it turns about its center of mass. And we include, of course, the translation, the linear translation of the mass of the system in this kinetic energy equation. And finally, the last one is very specific to just the slalom or the turning maneuver, is the yaw displacement. And you can think of this as just, I'm sitting in a nice rolly chair right now. So as I turn, my heading direction changes. That's an angular yaw displacement about my vertical axis. So rather than presenting all 4 of these metrics, however, we wanted to kind of summarize everything and make it as concise